All right, let's talk about the atom. But we're not just going to look at any old model of the atom. Today, we're taking the leap, the jump that took physics from a simple, almost mechanical picture into the truly bizarre and amazing world of quantum mechanics. So let's dive in.
So here's the big question, right? It's one of the first things you learn in science. Opposites attract. The nucleus in the center of an atom, it's positive. The electrons spinning around it, they're negative. So what's stopping them from just, bam, crashing right into the nucleus and wiping out, well, everything? This wasn't just a small problem. For physicists a century ago, this was a potential catastrophe for their theories.
You see, the first real picture scientists had of the atom was this kind of cute little solar system. You've got the positive nucleus as the sun, and the negative electrons as planets orbiting around it. Makes sense, right? But here's the fatal flaw. According to all the rules of physics at the time, an orbiting electron would be giving off energy, constantly. It would be losing speed, spiraling inward, and in less than a second, poof, game over. But obviously atoms are stable, so something was deeply, fundamentally wrong with the model.
So how do you solve this impossible problem with matter? Well, it turns out the answer wasn't in matter at all. It was in light. Yeah, to figure out why atoms don't collapse, scientists had to first figure out the true nature of light. And that turned out to be the key that unlocked the whole mystery.
So, before we can get back to our atom problem, we've got to take a detour. We need to understand light. And trust me, light is way, way weirder than you think. It has this secret identity, this dual personality that was about to turn the world of physics completely upside down.
I mean, just look at this spectrum. It's wild, right? That little sliver of rainbow we see, that's it. That's all we get to see with our own eyes. Everything from the radio waves that bring music to your car to the X-rays a doctor uses is all the exact same stuff. It's all light, just different flavors of it.
Okay, so when we talk about these waves, there are really two key things you got to know. Wavelength is just what it sounds like, the distance from the peak of one wave to the next. And frequency is how many of those peaks pass by a single point every second. So which one here has the higher frequency? Well, it's got to be the bottom one, right? The peaks are all bunched up, so way more of them are going to pass by every second.
And this all gets tied together in this super simple but really powerful equation. See, the speed of light, c, it never ever changes. It's a universal constant. So because c is locked in, wavelength and frequency have this inverse relationship. It's like a seesaw. If the wavelength gets shorter, the frequency has to get higher to keep things balanced. And that means more energy. Long wavelength, low frequency, low energy.
So at this point, physicists are feeling pretty good. They've got this whole wave thing figured out, or so they thought. And then a couple of experiments came along and produced results that just made no sense at all according to wave theory. These were the clues that really kicked off the whole quantum revolution.
All right, clue number one, the photoelectric effect. Sounds complicated, but the idea is actually pretty simple. You take a piece of metal, you shine a light on it, and electrons can get knocked right off the surface. Pretty straightforward.
But here's where it got really weird. The wave theory said if you just made the light bright enough, you'd eventually give the electrons enough energy to escape. But that's not what happened. You could blast the metal with the brightest red light imaginable. Think of it like a giant fire hose. And nothing. Not a single electron moves. But then, you shine just a little bit of faint violet light, and boom, electrons start popping off instantly. It had nothing to do with brightness, and everything to do with the light's frequency.
This puzzle completely stumped everyone until a physicist named Max Planck came along with this just out-of-the-box idea. He asked, what if energy isn't some smooth, continuous thing? What if it only comes in little chunks, like currency? You can have $1 or $2, but you can't have $1.372. He called these little packets of energy quanta.
And then, of course, Albert Einstein steps in. He takes Planck's wild idea and just runs with it. He proposed that light itself is made of these little energy bullets, which we call photons. Light is a particle. This explains everything about the photoelectric effect. A low-frequency red photon is like a ping-pong ball. It just doesn't have the oomph to knock an electron out. But a high-frequency violet photon, that's like a baseball. It packs enough punch in one single packet to send an electron flying. It's all about a single hit. One photon, one electron. That's the game.
Okay, so let's recap. Clue number one, light isn't just a wave, it's also a particle. Mind blown. But there was another piece to the puzzle. And this one came from looking at the light that atoms themselves give off when you pump them full of energy, kind of like what happens in a neon sign.
Now, you'd expect to see a full rainbow, right? A smooth smear of all the colors. But that is not what they saw. Instead, they got this Just a few sharp, specific lines of color. It was like a barcode, and every single element had its own unique, one-of-a-kind barcode. This was a huge deal. It meant that for some reason, atoms could only release very specific, pre-approved amounts of energy.
Okay, so let's put the pieces together. We know light comes in little packets of energy. And we know atoms can only spit out very specific packets of energy. So in 1913, this Danish physicist, Niels Bohr, connects the dots and comes up with a revolutionary new model for the atom.
But hold on. Before we go any further, we have got to do something really important. We have to completely throw out that old idea of the atom as a little solar system. Just delete it from your brain. It's wrong. It's a useful picture sometimes, but for what we're talking about now, it'll just get in the way. Bohr's idea is much cooler and much weirder.
So what did Bohr propose instead? Well, think of it like a ladder. An electron can stand on the rungs of the ladder, but it can't hover in between the rungs. Those rungs are the only places it's allowed to be. They're fixed energy levels. So for an electron to jump up to a higher rung, it has to absorb a photon that has the exact right amount of energy for that specific jump. Not too much, not too little. And then, when it eventually falls back down to a lower rung, it spits out a photon with that exact same amount of energy.
And this is really the whole game, right here. You've got two moves, absorption and emission. Absorption is when a photon comes in, gets absorbed, and kicks an electron up the ladder to a higher energy level. Emission is the opposite. An electron that's already excited falls back down the ladder, and as it falls, it releases that extra energy as a photon of light. That's where those colored lines come from. Each line is the light from one specific jump down the ladder.
I mean, you can't overstate what a huge deal this was. Bohr's model was a game changer. It solved the collapsing atom problem. It explained those weird atomic fingerprints. It was brilliant. But it wasn't the whole story. Science is always moving forward, and this incredible model had its limits.
Here's the thing. For hydrogen, with its one little electron, the Bohr model was perfect. The math checked out completely. But the second you tried it on helium, which has two electrons, everything just fell apart. The predictions were all wrong. It also couldn't explain the really fundamental stuff, like why atoms bond together to make molecules. It was a crucial, absolutely necessary step, but it wasn't the final destination.
So look how far we've come. We started with this little solar system that should have just collapsed on itself. Now we have this incredible quantum ladder for electrons. It answers our original question, but man, it opens up a whole new can of worms, doesn't it? If Bohr's model isn't the complete picture, it just pushes us to ask an even deeper, stranger question that leads to a world of quantum clouds and probabilities. What does an atom really look like?